So now it's time for questions, and maybe we will start with two reviewers. So maybe you guys want to start.
So are we doing all the just taking turns in question or just all the questions?
No, yeah, you do all your questions and then we.
All my questions. Okay, great. Thank you. So very nice speeches, Sarah. Very nice presentation. So congratulations to you. Can you talk a little bit about why you chose the unite and conquer approach versus rather than the divide and conquer approach?
Actually, we used another version of the Unite and Conquer approach. With the Unite and Conquer approach, you have different co-methods to solve the problem. They all have the main problem, and you have different co-methods. Here, it's the contrary. You have the same co-methods, same maximum instances, solving the same problem, but with different parameters. So they all can explore a wider range of solution. If we take only the divide and conquer approach, they won't have the whole set of agents, and the agents all evolve together in the same environment. So we just cannot have this divide approach. There is in the literature an approach which is more similar to the divide and conquer approach. You just divide the network into subnetwork. So let's say you have Los Angeles, you have downtown Los Angeles computed by a node, another part of Los Angeles computed by another node, but it comes with a lot of problems of communications. It's more rapid, but every time you have an agent leaving an area, you need communications to tell to the other nodes that another agent is here. So this approach already exists, but comes with a lot of problems. You have many libraries to solve specifically this communication problem. So we wanted to try something new.
Right. So can you tell me? So you talked about the fact that they all solve different problems because they have different parameters. How do you assure that the parameters you give them are different enough that you give different?
Actually, it's a very good question because in this work we had only 4 and 8 instances. We couldn't try with more. But maybe if we have many instances, it could be challenging to have every time more different approach, more different distributions. I think I didn't study how far we can go in the distribution of distributing weight, but this is a very interesting question.
Also, can you talk a little bit about how you validated your results? That you're getting the same simulation results.
Here, for example, if we let's take a simple one which is simple. Here, for example, with the for instance, you can see that in terms of accuracy, here you have right after the first exchange, you have already a score which is higher. A higher score means that the scores are higher. That means the agents adapt more efficiently to each other. So directly here you can see that even if just by comparing without checking any score, you can see that it's higher here. And you can see after 300 iterations, you reach a higher score, higher than with the traditional one. So this way we can say it's more accurate in terms of the results are more accurate. And in terms of convergence, we can see that we reach this score, and we also use the formula. The formula is here. I just add it in case of questions. We had a formula to assess the scalability. Again, in MathSim, you don't have a stop criterion. You just set the number of iterations that you want. And after you check visually, the traditional way is to check visually when you have convergence, as you have it here. In the literature, you have many works that try to develop a formula to check the iteration, and we relied on these formulas. The principle is simple. You just check the difference for the average score after, let's say, for 8 iterations, successive iteration, and if the difference between them, the successive iteration is under a small number, epsilon number, you can say that there is a convergence. So we check this. We have this formula that is validated after 1.5 hours or 45 hours with 8 iterations, for example. So we concluded that we have higher conversion, higher execution, higher results, higher precision, better convergence, better speed up, One thing we did also, I didn't present the results here, I presented only in my manuscript, but we wanted to make sure that the results that we have with multi-MATSIM are the same than MATSIM, because we need to have approximately the same. So we had, I worked with some people from IRT Systemics to check, because they work on MATSIM a lot, and to check how we could assess when you change MATSIM, you change something in MATSIM, you bring improvements, how you check if it's doing the same thing. And we check the volume traffic at certain hours. For one scenario, it was the same. We check the mod shares. The mod shares is very important. That means if you have in MATSIM, for example, 80% of people taking their car, 50%, 20% taking another mode of you need to have the same distribution for the mod shares. So this is how we validated our approach.
So you just mentioned that you know when you converged enough in some sense. So in the MATSIM, would you use that to cut off a simulation earlier? Because ultimately you're running longer, right?
Yes.
With your United
MATSIM. Yes.
Right. So my question is, if it was me, I would just look at these, converged enough and then stop the simulation. So why did you run it for longer?
Actually, first we didn't know really how to assess the convergence, right? So we just used the same approach as people who use the traditional MATSIM do. We just ran it for a certain number of iterations and check visually the convergence. And for the Los Angeles scenario, as I said, on the GitHub of the Los Angeles MATSIM, you already have some parameters that are set. So we just wanted to keep the same things to be the more near, the most same as possible as the MATSIM, traditional MATSIM. So we just did the same thing, and after we just visualized, as people do, visually the graph of the computation. Some people say there is a divergence about this subject. Some people say you need much more iteration. Some people say visually you don't have enough convergence. Maybe you need more. So there's not a consensus about that. But what we wanted to do with the multi-MATSIM approach was to replicate the result of MATSIM. So if you rely on score, for example, or the curve, we have the same thing.
Okay, and one last question. Can you talk a little bit about the complexity of information exchange between the multi-MATSIMs?
Yes.
Because that's probably where you're losing time, right?
Yes, exactly. We lose a lot of time, mostly in the one-person approach. The more you have agents evolving in a scenario, the more you have exchanges. So sometimes the exchanges take a lot of time. The different weights that you put, because you have distribution of weight that is different. Some strategies, when they are higher in terms of weight, make MATSIM longer in terms of execution. So yes, every 50 or step iteration, you have this exchange. So I didn't compute exactly. I didn't try to calculate exactly the complexity in terms of calculation. But yes, the more you have agents, the more you have instances, the more the complexity is high.
Yeah.
Okay, then we can switch to the next reviewer. Professor Taitsuke.
Okay, thank you. And maybe we can go back again to some more detailed questions.
If you want.
Okay, so that first, and actually I have many of the detailed questions, but before that, thank you very much for a very interesting presentation. So that in the top level question, I have two. One is actually it's something related to Eva's question. So that I'm also curious about the competition between the United Conquer and the Divide and Conquer. So I'm an HPC guy, so I'm always interested into how much totally resources are efficiently used. So in that either of the way, your goal is how to reduce total computation time with keeping the same or higher accuracy of the final scoring.
Yes.
So my question is that if you considering about resource means that in the parallel processing, also we can utilize a lot of number of the processors or
Yes.
GPUs.
Yes.
And just so this is not just a problem of the their accuracy and the computation time, but also the scalability on the system. So if you compare the United Conquer and the Divide and Conquer, so you only tested up to the 8 instances in the United Conquer approach. But if we have a much more number of the resources or processors, so how do you think that it's still the United Conquer is the hard advantage?
I think the Uniting Conquer approach is very efficient for maximizing the use of hardware resources. Here we use MATSIM, which is very sequential problem. You have some multi-threading in MATSIM, but it's mostly sporadic, not fully utilized. So relying on MATSIM for multi-MATSIM make us, I mean, we don't really take advantage fully of the hardware architecture. More with the distributed approach, we use distributed computing. But when it comes to a node, in the same node, it's true that because of MATSIM and the fact that it's not, as I said again, not fully optimized for the latest architecture, we don't fully exploit the hardware. So another work will be to enhance the multi-threading in MATSIM, enhance the parallelism in MATSIM to take fully advantage of the hardware architecture. But that's true in terms of one node with MATSIM. It's true that we don't fully use the possibilities brought by the hardware. That's why maybe we have very poor execution time performance on Fugaku, because with the CPUs on Fugaku, small CPUs, mostly for parallel intensive applications, it doesn't work well with a mainly sequential program like MATSIM.
Okay, so about the Fugaku processor, I will ask again for the more detailed question. Okay, so that my second question is about the surrogate model, which you called it, and you introduced the AI or neural network technologies. So that further, you tested that case with 1% LA model, not the 0.1% LA model.
No, we use the 0.1%.
Oh,
actually, yes. To have, how to say that, to minimize the chances having the repetition of the same agents evolving together, we just extracted 1,000 agents from a bigger scenario. It was possible to extract it from the 0.1% scenario. Actually, it's exactly the same. With the 1% scenario, you just have more agents, so you minimize the risk of having, in a repetitive way, the same agents evolving together.
Okay, so that maybe I misunderstood about that, but my question or curiosity is that did you, even with 0.1% model, did you check that first the complete simulation of the model without a surrogate model and with surrogate model? So how did you compare the accuracy of the simulation?
Can you repeat the question again?
So my question is that without introducing the surrogate model, they do the same thing even with a smaller 0.1% model. And did you check the accuracy with or without surrogate model? So complete simulation or supported by the surrogate model simulation. Of course, that one is much shorter computation time. I know.
Yes.
So how about comparison in the accuracy?
Actually, I didn't compare it with true execution of MATSIM. If I understand well, your question is that did you compare the results with the real MATSIM, the traditional MATSIM, with the results you have with the approximation of the surrogate model? I didn't. I just relied on, because when you compute with the test data, when you check the residuals, you check with the real data, right? And this is the way you calculate the MAE and the MSE. So I just relied on the false positive and false negative to test the approach.
So you tested it indirectly, the result with residual and other data.
Yes. Yes.
Maybe you can believe that the result,
yeah,
even with a surrogate model. Okay. Okay, I have some more detailed question, but then I will stop here just now.
Thank you. Then maybe we can go with our online guest, Alexandre.
Hi. Thank you, Sara. That was very interesting. It was great to see the benefit of Unite and Conquer that made invented for against solver transfer to agent-based transport simulation. I know there are multiple ways. So you did a great job at comparing the unite and conquer versus divide and conquer. But in the realm of unite and conquer, there are algorithms that can enhance this. For example, evolutionary algorithm, where you maintain a population of solution, and instead of discarding one solution for another based on the score, you could try maybe to recombine them, create an offspring that attempt to keep the best of both. Is this something you've considered in your work? What's the rationale for sticking to the discarding the worst solution and just moving forward with the current approach?
Actually, for the work I achieved so far, I didn't really think about trying with another method, but it's a very good suggestion. Thank you.
Sure. And now I'm an HPC guy too. My background is in that area, and I would like to put that a little bit more in perspective of the implementation aspect. I know you focused on the method, obviously, but the MATSIM is written in Java, and usually Java is notoriously a little bit slow in HPC. I'd like if you could talk a little bit more about how you put your results in perspective of an implementation that would potentially leverage more HPC-friendly technologies like C++, GPU acceleration. Do you expect everything to transfer as is, or would you nuance the learnings there for language and techniques that are a little bit closer to the hardware?
Actually, this is exactly what the authors of Maxim are trying to do, switching to the C++ mods, because they already tried to use the MPI with the Java maybe 5 years ago. Don't really remember exactly, but there was a problem. I don't know if it's still the case, but there was a problem with the MPI for Java, so they couldn't achieve to do this at this time. But now they are considering many things. They are considering exploiting more the multi-threading because, as I said, it's very sporadic. They are considering using the divide and conquer approach to have distribution computation, divided the network into subnetworks, for example. So this is exactly what they are trying to do right now. But yes, I thought about it at the beginning. It was a little challenging for me, so I was first focused on the algorithmic approach, focusing more on the design of the algorithm. But yes, this is something I considered.
Makes sense. One last question, maybe on what's next for your work. Is this open source? Is this going to be integrated in MATSIM? How do you envision this in the future?
I hope. I know the Maxim authors knew about my work and they were really interested. I have a contact. I don't know if I will still work on this subject after, but I will do I will go on with the postdoc. Maybe I will continue to work with that. And if the Maxim authors are okay, I will. In any case, I will publish my code on GitHub and it will be accessible. So yes, of course, yeah, I will be happy if it could be integrated with Maxim. But yes, this is something I consider also.
Awesome. Well, that's all for me. Thank you, Sara.
Thanks.
Thank you, Alexandre. Mark, we can continue with you.
Yes, thank you, Mr. President. First of all, I would like to congratulate you on your work and your very clear presentation. Your slides were very clear and well illustrated. You have well presented your contribution and in a very convincing way, but it appears to me a little bit technical on one hand. So I have three questions, maybe simple to formulate, but maybe the answer is not so easy for you.
Okay.
First of all, I would like to go back to road traffic or traffic simulation. Why is it hard? Because in some sense I saw that you have only a few thousand or 100,000 agents.
Yes.
And in agent-based simulation, we reach easily millions of agents. So what is the algorithmic complexity? To what problem is it related? First, before putting it into MATSIM, can you go
Yes.
back on the difficulty of the problem?
Of course. The main difficulty, I don't think that the difficulty is the agent simulation itself. The main difficulty is that most of the multi-agent traffic simulators don't take advantage of the latest hardware modern hardware architectures. That's the main problem. You have, like as I said, Maxim has 20 years. At first, they didn't focus on performance. They just wanted something, a multi-agent traffic simulator that works. So that's why maybe they choose Java. They didn't care about the performance. Now we have new things. We have more people in the traffic. We have IoT in the roads. So we need this multi-agent approach. And this multi-agent approach is very challenging because the road traffic agent now don't take fully advantage in terms of implementation. You don't have HPC techniques. You have sometimes, as I said in Maxim, you have a little of multi-threading. They don't take advantage of distributed computing, for example. This is the main problem. So my answer to this question will be, the problem is not the multi-agent traffic simulation, but the tools that which are not adapted to, which are not modern enough and don't take advantage of what we have now in terms of hardware and also implementation techniques.
This is quite technical because my idea is the following, to ask you the second question, is if you have heard about Uber technologies and Uber working quite well to deliver taxis or deliver pizzas, and they use tiling. You know, they tile the space with hexagonal, because mainly when you're doing some traffic simulation for planes or for just cars, so you have to compute shortest path under constraints, so this is why it is difficult. And you have to compute coordinates which are real numbers. So each time you have two locations, so you have a new computation to be made, and
real time.
there are infinite positions.
Yeah. It's real-time computation, right?
So each time you have a distance computation between x, y, and
of course.
And when you do tiling, so you do what is called compactification in mathematics. You have an infinite space which go back to a finite number of clusters. And then if you have a hierarchy of cluster, which is Uber H3 designed for computing a finite number of location destination, you only have a finite number of computation to do, so you can really make your agents very efficiently find one destination from one location. So do you believe the algorithmic approach for improving road simulation is more looking out of the tools and improve with HPC for larger multi-agent simulation? Have you investigated this kind of ideas?
Actually, what you were talking about with tiling, is tiling the right word? I didn't know about it, to be honest. What I know, it makes me think of just what we have with Google Maps or Waze, for example. You have real-time traffic management, right? But the problem with this type of tools is that you need humans to use this. They need you to simulate the traffic. For example, I have an anecdote about this. You have a guy, a German guy in Berlin. He had I don't know the word in English, but he just had on him hundreds of smartphones with Waze on it, right? So he created a fake jam traffic with his. So in this way, it created a real traffic jam, because when you, as a user, you see there is a traffic jam in this direction, this is what happened. You just choose another way, so they all choose another way, and you have a real traffic jam. Here, this kind of traffic simulators are more for example, cities. Here, for example, the IRT Systemics right now is working with Maxim to check how the new subway here, the line 18, I think, I don't remember, will have the influence that will have on users. So you use traffic road simulators based on multi-agent for this type of thing. And it's totally autonomous. You don't need other humans to turn on their phone to check things, right? It's totally, how to say that, independent to the usage of other persons. So this is two different paradigms.
I agree, but maybe you look at H3 design of tiling and you better understand what I mean. But
what I mean by that is that I think, I'm not sure, but I think I understood the question. What I think is that this type of simulation that you're talking about, they have no problem in take advantage of HPC hardware and techniques, right? But it's not the case for this type of simulations. This is why we try to bring new designs for the algorithm, for example, in this kind of traffic route simulations. I'm not sure I understood your question, but
Yes, so we can talk a little bit later about
okay.
that.
Thank you.
My third question is about, here's a scenario. Scenario are made at agent level, right? They
Yes.
try to accomplish their
Yes, the daily tasks. Yes.
So now, if I'm an agency or government, how do I set a scenario? Because usually what I'm interested is I have a specific question and the scenario is addressing this question.
Okay.
So can you tell me
Yes.
a little bit how
Of course. Yes.
I can make it?
Again, with MATSIM or other traffic road simulators, you have a modelization of what's happening. So if you have a sample of the population, we'll have a global behavior of the population, right? So, for example, you as let's say you are a MATSIM user, you want to use MATSIM and you want the daily plans for an agent for a city you want to simulate. If you do the same thing, the same way they did, they just went to cities, collectivity cities, to have some information about the behavior of the population based on census data to make the plans of a certain sample of the population. So basically, it's just based on census data.
So I think it's okay for me.
Okay, thank you. So I will ask a few questions myself. I would like, maybe to go back on the communication strategy.
Yes.
Can you maybe give a bit more detail of what exactly is the information you exchange between all the model? And then did you try to modify the information you exchange to see, maybe to have a trade-off between the volume of information and efficiency, or to see what was the most interesting piece of information to exchange?
Yes, of course. Just go back to the exchange in multi-MATSIM, sorry. So again, as I said before, the instances have the same information. They have the same set of agents and they have the same city simulated, for example, for Los Angeles or Paris or anyway. They have exactly the same information. So what they try to do, they just try to explore different range of solutions and just exchange to each other which are the best, which one are the best. Here, for example, here instance I and J have exactly the same agents, but here we focus, to have clearer explanation, we focus just on one agent. The agents at the beginning of the simulation have the same plan. You have exactly the same plan. But because of the different distribution of the waste strategies, they will generate, during the step iterations, they will generate different plans. For example, first iteration, you will have the simulation over 24 hours. Then you will have another plan generated with other strategies. You change the departure time, you change the mode of transport to have a better time efficiency in your day. So this is what happened. Here you have, after 50 iterations, here you have a plan, and here you have a different plan. This plan have a score. So since there are only two instances, both are have this different score. What is a different score? Different score means that a higher score means that the time of this agent is more efficient, right? There is no loss of time in this plan. Let's say I has the best score, right? The score is 100. I just say this, it's just an example, and this one at 50, for example. Here, I have the best score, and since I is like, I have the best score, so I will continue with my plan because it's the more efficient. So I will continue with another 50 iterations to generate other solution to try to reach a higher score. Here, I have only 50, the other have 100. So maybe it will be better to continue with the plan of the other because it's more efficient. So I will continue. I say it here it's 100, here it's 50. So there's no discussion. It will just take the plan of the other and continue. But if the difference is not very high, we compute it with standard deviation. Let's say this one has 100 and this one have 39, 99, for example. There is only a difference of 1. It's not the best score, but it's very near to the best score. So no need to change. I will just continue with my unscore. So actually, there is a process where After each step iterations, you have an exchange of vectors to check which one of the instances, because here is an example, there are only two, but you have a they have a computation to check which one has the best score, the standard deviation, should I get the score of another instances, etc.
Then can you show again the curve of the
Yes.
of the model? No, after where you have all the where you compare.
Sorry, my results. Okay.
Yes. Yeah, this one. Because it seems that the simulation, so the baseline model is behaving a bit differently because the score is decreasing at the beginning and then it's increasing after. And then it doesn't seem to, I mean, it's hard to tell, but it seems that the Unite and Conquer model has a higher rate of convergence, and even that if you let run the baseline model, it would not reach this. So how do you explain that?
As I said, here with the baseline, you have, let's say, in the first iteration, you have a plane. They all have the same plane, right? Here in the baseline, Maxim has a space for 5 planes for each agent. So one iteration, you have a new optimized plane. The other iteration, you have another optimized plane until 5. And every time, Maxim will try and one plane, another, one plane, another. Here, since all of the instances focus only on one plane, have not 5 planes in the memory, they only focus on one plane. The score is increasing more rapidly. And here, because you have here 4 instances, all are trying to explore space of solution, and here they exchange just, okay, I have the best solution, I have the best solution. They all exchange the information, you explore more, a wider space of solutions, and they all take the best one or continue with their own if it's not very far from the best one. So the short answer to this question would be they just explore a wider range of solutions. That's why you have.
But would the black curve converge to like 115 if you let it run long enough?
Oh, yeah, of course. But you can, I mean, you can let it run enough. You can let it run for 1 year, but you can also let this one run for 1 year, and they will all have higher score than the traditional one.
And it also seems that it's very different at the beginning. Is it due to the various parameters you set up for the various models?
Yes. For example, sorry. Go ahead.
No, so if you, for example, if you run the baseline model, but with the parameter you use for the blue curve here, would it go higher?
Actually, if you take the instance 0, which is the green one,
Yeah.
it has exactly the same parameters as the traditional one. The only difference is that this one focuses only on one plane. Every time after iteration, it focuses only on one plane, whereas this one have until 5 planes to explore. So it will be slower to have the same results.
But then why don't you use the baseline model with one plan?
Because with the baseline model with one plan, you will have this this evolution, and it won't. You won't have this jump. It will be more rapid than this one, right? But it won't be as rapid as this one because here you have other instances trying to explore more solutions. That's why.
Okay, thank you. And yeah, and then can you explain how, so with the surrogate model, you tested only part of the problem?
Yes.
And how would you incorporate that in the global model to try to make it go faster?
Actually, I didn't. The main goal was not to have like intermediate results to incorporate it matching. This was not my goal. It is a good idea, but this was not what I wanted to do. What I wanted to do is to have a tool for having an approximation of the results of Maxim. But this is very interesting. We could try to incorporate intermediate results in Maxim. Yes, of course.
Thank you. That's okay. Did you want to?
Yeah, okay, so I'm also the system guy, so I'm very curious about your implementation. But before that, so you mainly, today's presentation, you mainly focus on the UC methodology and also that how to utilize such resources. But in your total, your full dissertation, I'm curious about, you mentioned two things. One is GPU implementation, and the other one is parallelization with MPI, that is a multi-map sim. So I wonder that this kind of the simulation for each part of the UC model is then really fit to the GPU acceleration. So it is understandable that the CPU works well, but GPU's acceleration is something different. So why do you think that GPU is also available to accelerate your work?
GPU could be a good idea for many tasks. For example, for calculating the itinerary from point A to point B, right? It could be a good tool because you have SEMD instructions in MATSIM. So it could be very efficient. You already have multi-threading also in MATSIM. Actually, there are a lot of works in the literature combining CPU and GPUs programs, and it's a good idea. I didn't try it. I saw that there are some challenges with the communication between the CPUs and GPUs, but to be honest, this is something I didn't really had the opportunity to explore.
Okay, so that my curiosity is that, so that as you know, the GPU is based on the SIMD model, and there's some limit or minimum number of the operations should be taken in the one clock because there are the 32 or 64 cores are working together in the SIMD. So that I'm wonder that in the basically the sequential execution of the original MATSIM, how much SIMD level spatial parallelism exists, then you can apply the merge task or something. So nowadays, advanced GPU like NVIDIA's have a lot of feature to support the merge tasking also, with dividing the thousands of the cores into the several chunks. But my basic question is that the single sequential execution of the MATSIM is still good for the SIMD model or spatial parallelism on the GPU. So if there is no such a chance, GPU doesn't work well even for the MATSIM. So do you have any opinion about that?
So what is the question, sorry?
Question is that original MATSIM is a sequential execution, right? And but then even using the merge tasking on the GPU, each task has at least some level of the spatial parallelism to utilize the SIMD model, so that that single sequential execution of the original MATSIM is really fit to that single thread of the execution in the GPU. That's my question.
Okay, I will try to answer to the question. Actually, as I say, there is some multi-threading in MATSIM. It's sporadic, and I think it's not fully exploited. I tried to set, for example, much more threads in MATSIM, and I have the same results with 20 or 40 threads, right? So I'm not sure it's working fully, but when it comes to trying to take advantage of the GPUs in terms of sequential execution, to be honest, I didn't know that. I didn't really focus on that. So thanks for your suggestion. I will check if I can do something with that. But that means we could have better results also with the SVE maybe technology with the Fugaku, right? So okay, I didn't know that. Thank you for the suggestion.
So SVE is a very short, there are SIMD like an 8 to 16 operations, but the GPU is much more.
Okay.
So the second question, maybe this is not a question but a comment about the A64FX Fugaku processors. So that you mentioned that the Fugaku processor is designed for the really massively parallel with up to 150,000 of the nodes in the Fugaku. But you tested just a single node of the Fugaku versus single node of the Intel Xeon,
Yes.
right?
Yes.
So that my opinion about the architecture of the Fugaku is actually not good at to have such a really large scale system. But they focus, and I'm a part of the working group of the design of the Fugaku processor. So I know everything about the inside. So my opinion that the first purpose is how to reduce the total power consumption, even keeping the 48 cores in such an early 7 nanometers technology. So it is not just focused on the really large scale parallel processing. Of course, ultra large scale parallel processing system must focus on the power consumption. Yes. But the big difference between the Intel Xeon and Fugaku's A64FX is how to reduce the power consumption, keeping the maximum performance of the flops. Their maximum performance are almost the same like 3 teraflops, but the Fugaku's processor is reducing the power consumption. And on the payback, they lost many things, like, for example, very long instruction pipeline. It's 8 stages. It's extremely long. And also, there are the shortage of the registers, especially for the shadow registers. So usually, we must design the long pipeline to cover that. The more number of the registers, but the Fugaku doesn't have enough number of the registers. So I think that is why you have a slower performance compared with the Intel Xeon.
Okay. So
that's just a comment.
Okay. So for you, is it still specific to the ARM architecture, or there's
no,
nothing?
ARM and the x86 is not a problem.
Okay. Okay. Thank you.
One more.
Yeah, please.
Small, very detailed. So you also talk in the first part, the Unite and Conquer has some robustness because it is just spreading the multiple their way, like for example, 4 instances or much more. And if you lose one instance in some failure, it's okay. But and technically, you use the MPI for this implementation.
Yes.
So in the MPI, if you have a collective communication with collecting the order result with maybe altogether or something, one process failed, it's stopped.
Yes.
So that then only the way is that using the asynchronous collective communication on the MPI. Yes. But I guess you didn't do that.
Yes. Actually, for the synchronous communication, we use the MPI altogether, the collective communication. But for the other type of communication, to have the non-blocking side of the communication,
yes,
we don't use the collective communication. We use, like, you send a message to the other to continue the process even if one is failing.
Yes, but another problem of the certain non-broken communication or collective communication is that the answer is not coming. So is it by failure or just a slow down of the computation? So it is a problem.
Yeah,
so,
that's true.
Still, I think your idea have some open question about that part.
Yeah.
But, logically, it's true that you have a robustness of the communication or parallel processing, but it is not. In my understanding, it is not completely implemented in the system.
Yeah, exactly.
That's not a fundamental problem, but only the problem of the implementation.
Yeah.
That's it. Thank you.
Thank you.
So maybe we can finish with Naid, which was the supervisor of the PhD.
So, thank you, Monsieur President. In fact, evidently, I haven't question now because we worked together and we did. You responded to all of my questions. So, but I would like to say just some word about the project, about the scientific project. Approximately 4 or 5 years ago, I defined this project with Jean-Michel Bateau, who is here present here. In this time, he worked in FH company. So we decided that this project, in this project, we will use one or more existing multi-agent simulators. So, but the problem, definitely we decided to use MetSim. But in the first, we had especially Polaris multi-agent simulator. This multi-agent simulator was open source, but it changed the statute during the first year of PhD of Sara. So we opted finally for MatSim, and but this was a problem because MatSim is a very good simulator for the reason that Sara explained. But the problem, it was especially Java programming language. And this is a problem added to the complexity of the code of this multi-agent simulator. So it was a very difficult work for Sara. And I think this difficulty is also added to the difficulty of the advisor company of Sara, because as I said to you, Sara changed 3 times. It's not Sara, but the company changed 3 times the advising of this PhD. So it's not very stable situation for doing a PhD calmly. So I think despite of all this difficulty, Sara prepared her work and implemented her ideas in academic, industrial, and also international context. It's a very good implementation of ideas. I would like to say that for me it's a very good work. I hope that the jury members are agree with me, but because it was very difficult, especially because of Polaris and the structure of MatSim. And also, I think I see my notes. I don't want to forget to say that what I appreciate particularly for the work of Sara, apart from the scientific part, it's the philosophical approach that you use for working science. And I like very much. And especially, I would like to say that for Unite and Conquer approach, techniques, Sara proposed some things, she has a reflection, personal reflection about Unite and Conquer in her manuscript that I think is very interesting, to saying that the core methods work in symbiose, I don't know how to say it in English, to obtain, to achieve an objective. It's very good. Thank you. And congratulations for your work.
Thank you so much.
Okay. Thank you, Naid. So now if there's no question in the audience, we will ask you to leave so that the jury can deliberate.